Assalamualaikum. Today I want to present about the table 1 of closed loop system. For the first is we try to show the mathematical calculation using characteristic equation. Okay, this is the sketch of the pole 0 for the pole 0. Okay. Okay, the second, use the MATLAB software to confirm the answer. So the first thing first, we declare the sim s, and then we use the function, we substitute as a g, and then use the transfer function, which is 1 over 100, which means the 1 is s square 0 0. Okay, next we use the command pzmap to show the pole 0 map. Pzmap the g as we substitute, then we hit enter. Then this is the pole 0 map. Okay, based on findings 1 and 2, determine whether the system is unstable or marginally stable. The system of control closed loop system for number 1 is marginally stable. Okay, for the second objective, this is the circuit, and then we need to simulate the table from the table. Okay, we will run the simulation. The step is time is 0. Okay, let's try to run. Okay, this is the graph from the equation is 1 over s squared. Okay, from this we can see the constant oscillation, which is sinusoidal wave, and then there is the graph is marginally stable, and then the overshoot is 0, is can define the rising time, can define settling time, and steady state error is 0 too. Okay, for the objective 3, okay, they ask for PID controller, then we add the PID controller. We add in the block. Okay, from the circuit we must use the PD controller. Then we double click the PID controller and change to PD controller. Okay, the proportional we change to 10, and derivative change to 10, and then the filter coefficient we change to thousands. Okay, then apply, hit OK, and then we run again. We run the simulator again. Okay, this is the first graph for table 1 after we add the PID controller. For overshoot, we measure we graph over the line, which is this time, which is this. Okay, for the value overshoot, okay, we can see at the value side, which is the first is 1.070, which is at this peak, and then we subtract with value at steady state, which is 1, and then divide by 1, and then times by hundreds, and then we get the 7% of overshoots. Okay, in the graph for settling time, which is we can define by the graph, where we set the value at 0.98 and 1.02. Okay, from this graph we can define the settling time at when we zoom in, and we can see the literal function graph is touching by the time we set, which is 1.02, and then we get 1.74 seconds. Okay, for the rise time, we must search for 90% and 10% of the graph. Okay, for the value, we may change to 0.9 and the value, another value is 0.1%, and then we get the time, the rise time from 0.014 second and 0.186 second. Then we subtract the second value, subtract to first value, which is 0.186 minus 0.1014, and we get 0.172 seconds. Okay, the steady state error is, when we come to steady state error, we can see that the steady state error is so discrete, and approximately the steady state error is 0.001%. Okay, that's all from me. Thank you.
Assalamualaikum and hi everyone. My name is Aziz Tazri bin Faizli. My matrix number is AA200719. So right now I'll be going to do the video for my group, which is how I solve the objective 1 to 3 for control closed loop system number 2. So without further ado, let's go. So the first objective will be to determine stability of a closed loop control system using pole zero plot. So we go. So this is the system number 2. So what we're going to do first is we need to declare the G1 block, so the transfer function block. So ini, and then we use the bracket, and then we declare the numerator. It will be 20. And we close it. Then we open another bracket, and it will be, the value will be 1, 2 and 9. Close the bracket. So it's the same with this. Then what we're going to do is use the command pzmap and declare the block, which is G1 block, and press enter. So this will be the pole zero map. So we need to drag it to find the mark. So this will be the value. So this will be the value. So this graph is marginally stable. So we can close it, and then we go to the second objective, which is to simulate the closed loop system to obtain the start response. So to do this, we need to go to the Simulink. So this is the Simulink that I have prepared beforehand. This is the step, this is the subtract block, the transfer function block, and the scope block. This PID will be used for later purposes. So you need to connect it like this, and then declare the transfer function block, and then we just run the program. So then we click the data inspector, and this will be the data that we achieve for the second objective. Here we need to calculate the overshoot value, the settling time value, the rise time value, which is here, and the system error, which is around here. So with that out of the way, we move on to the third objective, which is to implement P, PD, PI or PID controller to meet control system design requirement. So here I decided to use the PID controller. So let's go to the Simulink. So here the PID, we need to adjust the proportional value to 10. The integral value also need to be 10, and the derivative value needs to be 1. Then we apply and click OK, and then we need to put the PID controller in between the subtract block and the transfer function block. So now we run. We click the data inspector. So here you can see the difference. The new graph here is with the PID controller, and the graph below it is before we implement a PID controller. So as you can see, it has a much bigger impact with PID controller. So here it's the same. We calculate the rise value, the overshoot value, the settling time, and the system error. So that is all for me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Adil Hakimi bin Ismi, and my matrix number is AA2090. So for today, I will continue for closed loop system 3 for objective 1. So for objective 1, we need to do mathematical calculation, command windows, and answer the question that determine whether the system is stable or unstable. So firstly this is my Simulink that I have built that have step, subtracts, transfer function that is 250 divided by s to the power of 2 plus 4s plus 50, and the scope. So this is the mathematical calculation that I have made. There I get the zeros equal to zeros, and the poles I get is -2 plus 17.2i and -2 -17.2i. So for the next is our MATLAB command. For our MATLAB command, first we need to type h equal to tf 250, 14300, and we will get a transfer function like this. Then we type pz map h and grid on, so that the grid will on the map. You can see on our here. This is the pole zero map that I have got. And for the final question, whether the system is stable or unstable, the answer is the system is stable in figure 1 and 2. You can see the poles on the left side. The x-axis and y-axis both have zeros at s equal to 0. That's all for objective 1 closed loop 3. Thank you. So I will continue for closed loop system 3 for objective 2. For objective 2, first we need to change our step to 0. Then we need to run. And then we need to enter command window, that is g equal to tf 250, 1450, and we will get continuous time transfer function like this. And then we enter a new command that is t equal to feedback g, 1, and we will get continuous time transfer functions like this. And enter the command t equal to 0.01, 10, and step t, t to get the graph. And then we will get the graph like this. For step response, it will start from 0 because of our step we have changed for 0. This is our step response system in Simulink, and this is system response closed loop system in MATLAB command. That's all for me for activity objective 2. Next, for closed loop system 3, objective 3, the command window for closed loop system 3, objective 3 is g2 equal to tf 250, 1450, and you will get continuous time transfer function like this. And then we enter command that is g1 equal to PID 1010.1, and we'll get transfer function continuous time PID controller in parallel form. And then we type g equal to g1 multiplied by g2, and we will get continuous time transfer function like this. And t equal to feedback g, 1, and you will get continuous time transfer functions like this. And then we enter t equal to 0.01, 2, step t, t for the graph, and S equal to step in for T. So we will get the rise time that is 0.0082, settling time that is 0.0131, settling mean that is 0.9008, settling max that is 1.0160, overshoot 1.6 and undershoot 0. We get peak 1.0160 and peak time is 0.270. So the graph that we get from this function is like this. This is the graph that I get after I plot for X and Y. So that's all from me for auditor 3. Thank you.
Assalamualaikum and hi, my name is Muhammad Iqbal Azri bin Zainuddin. Now I will present about closed loop system number 4. Okay. So I will present objective 1, objective 2, and objective 3. So go to for objective 1. So PS equal GS per 1 plus GS HS. So using this formula to calculate the transfer function. The denominator is the characteristic equation. By letting the characteristic equation equal to 0, the roots which are the 0 and equal can be obtained. Okay. So now we for the closed loop transfer function. Okay, for GS equal to 250 per S square plus 4S plus 50, while the HS equal to 2 per S plus 2. So using the formula TS equal to GS per 1 plus GS HS, so we can get 250 per S square plus 4S plus 50 multiply 1 per 1 plus open bracket 250 per S square plus 4S plus 50 close bracket open bracket 2 per S plus 2 close brackets. After the value for the formula. So after that, for the question, the answer is 250S plus 500 per S power of 3 plus CS square plus 58S plus 600. So we can get the characteristic equation from the answer. So the characteristic equation is S power of 3 plus 6S square plus 58S plus 600 equal to 0. So we can get the root negative at 0.05 for the roots is 1.03 plus J 8.57, 1.03 negative minus J 8.57. So for the pole zero plot, like this is CAW. Below is the root locus graph of the system obtained from MATLAB. As can be seen, the calculated value are almost exactly the same as the value obtained from MATLAB. So this is root locus. Okay. Find there are two root located right half plane. The system is stable. So end of for objective 1. So go to objective 2. The for closed loop system was built by MATLAB. So I built the closed loop system number 4 by MATLAB. So you can see has a step, okay, function 1, 2, and scope. After running, so after I built the closed loop system by MATLAB, I running the simulation and the response below. Okay, the response like this. So from the graph I can answer the question lah. Okay, for system number 4, the graph is unstable and the overshoot, rise time, settling time, and steady state error is none because it is because the value could not be calculated. Okay, so enough for objective 2, go to objective 3. So PID controller for objective 3 is the PID controller that was added into the simulation as below lah. So we can see PID controller in the closed loop system. Okay. The value of PID are taken as shown below. So KP, you can see KP equal 0.01, KI equals to 0.12, and KD equals 0.01. So for the graph after the simulation, the nearest time graph, and from the graph you can determine the overshoot, rest time, settling time, and steady state error for closed loop system 4 after add the PID. So the overshoot is 0, rise time is 2.25, settling time is 4.49, and steady state error is 0. So that's all for me. Thank you. Assalamualaikum.